Hello everyone, and welcome back. Today we're going to continue our exploration of fractional calculus and consider a problem you may have encountered in single variable calculus, in particular iterative integration. So iterative integration can be viewed as the inverse process of taking derivatives multiple times. For example, the first, second, third, and fourth derivative of a particular function, but instead of taking the nth derivative of a function, you can take the, say, nth integral of a function, and that's what some people refer to as iterative integration. And a very interesting application of iterative integration actually gives rise to one of the natural fractional integrals and fractional derivative operators that we're actually going to be working through this series with, and that's called the Riemann-Liouville fractional integral and the Riemann-Liouville fractional derivative. And actually we have seen a couple of their properties, and we'll talk about them today as well. So let's sort of motivate what we're going to be doing here today with some basic single variable integrals that you probably already know how to do, but we're going to be notating them in a slightly different way. So I'm going to define the operator I1x of the function the natural log of t to be equal to the integral from 1 to x. So 1 is what we're going to be referring to as a base point. X is going to be referred to as the terminal point of this operator I, which is an integral operator, and they're going to, of course, correspond to the lower and upper bounds of our integral that we're going to be working with, and we're going to be applying this operator to the function the natural log of t, and then we're going to be integrating with respect to t. So we should already know the answer to this particular integral. That's just going to be equal to t natural log of t minus t, and then we need to evaluate this as t goes to x and as t goes to 1. So once we evaluate that, well, what will we get? Well, that's just going to give us x natural log of x minus x plus 1, and that's going to be the result of this particular operator of the natural log of t function. Now what we want to do is we want to apply this operator to this again. For example, let's assume we're interested in the operator I1x2 of the natural log of t, and we're going to be defining this to be equal to the integral from 1 to x of the integral from 1 to x1 of the natural log of x2 with respect to x2, and then finally x1. So we should already know that this integral on the interior of the primary integrand is actually just going to be equal to the integral from 1 to x of I1x of the natural log of x evaluated at x is equal to t dt. Those integrals are precisely equal to each other, so therefore this operator that I'm sort of implicitly defining here is just I1 of x of I1 of x of the same exact function. So what we can do is we can just replace the answer that we got before. So this is just going to be equal to the integral from 1 to x of t natural log of t minus t plus 1 dt. So we should easily be able to do the integral of minus t plus 1. That should be an issue. And in order to do the integral of t natural log of t, what we can do is let u be equal to t and dv to be equal to natural log of t, which is the same as I1x of natural log of t. So pretty much we can apply an integration by parts relationship there. So once we do all that algebra and simplify, that's going to give us, before we evaluate the lower and upper bounds, of negative 3/4 t squared plus 1/2 t squared natural log of t plus t, and then we can evaluate this as t goes to x and as t goes to 1. And then once we clean this up a bit, that's just going to be equal to negative 3/4 x squared plus x minus 1/4 plus 1/2 x squared times the natural log of x. Right? So that's going to be equal to I1x2 of the natural log of t. Right? So one may be even adventurous to maybe see, okay, well, what would I1x3 going to be? So obviously we're going to have x cubed there in front of that natural log of x. We're going to have some coefficient there, and then we're going to have some polynomial that sort of precedes that, right? At least that's a conjecture, right? So maybe you want to try that on your own, and that shouldn't be too much of an issue. Just a double integration by parts formula there, but that shouldn't be too much of a hassle. So let's see if we can try to generalize the operator that we're actually working with here. So what we're going to do is we're going to define this operator, I, base point A, terminal point x of n of f of t, to be equal to the integral from a to x, integral a to x1, integral a to x2, all the way down to a xn minus 1 of f of xn dxn dx minus 1 all the way out to dx1. Right? So that's going to be our iterative integral operator. So there's a nice little theorem that you may have encountered in single variable calculus, and that's the following. In particular, this operator that I've defined here is going to be equal to 1 divided by n minus 1 factorial times the integral from a to x, so it's that primary integral that we're working with, of the function x minus t to the power n minus 1 f of t dt. So instead of doing those n integrals out, you can actually just evaluate a single integral that is equivalent to doing the iterative integration process. And this formula is sometimes called the Cauchy formula for integration, and you can easily prove this via the fundamental theorem of calculus, mathematical induction, and possibly Leibniz rule, depending on sort of how you go about doing that. So let's just do an example of what that actually results into. So let's assume that we're interested in doing I01 of n, for example, t to the power of m. So we want to evaluate the iterative integral of a polynomial function at a particular point from 0 to 1. And we're going to let n and m be arbitrary integers. So if we use this formula directly, that's just going to be equal to 1 divided by n minus 1 factorial times the integral from 0 to 1 of, so x is going to be evaluated at x is equal to 1, so we're going to have 1 minus t to the n minus 1 and then t to the power of m dt. So what I want to do is I'm going to rewrite this in a familiar way. So that's going to be what? So this is going to be equal to 1 divided by n minus 1 factorial, integral from 0 to 1, and I'm going to put my t to the m in the front. I'm going to write it as t m plus 1 minus 1, because 1 minus 1 is just going to be 0, so that's going to be equivalent. And then we're going to have 1 minus t and then n. I'm going to just sort of group that by itself, minus 1, and then dt. So you should recognize this particular interval from single variable calculus because it's an integral from 0 to 1 of t to the a minus 1 and 1 minus t to the b minus 1. That's precisely just equal to a beta function. So that's just going to be equal to 1 divided by n minus 1 factorial times the beta function evaluated at n plus 1 for the first parameter and then n for the second parameter. And we know a very nice property relating to the beta and the gamma function, and that's going to be equal to 1 divided by n minus 1 factorial times gamma of m plus 1, gamma of n, and then gamma of the sum of those two things, so m plus 1. So what do we have here? So remember that gamma of n is just m minus 1 factorial, so those two terms cancel out. And let's assume that m and n are both natural numbers. So if that's the case, that means gamma of m plus 1 is just going to be equal to m factorial, and gamma of m plus 1 is just going to be equal to m plus 1 factorial. So that means we have the result that I01 of n of t to the m is equal to the constant m factorial divided by m plus n factorial. And one may be even ambitious to extend this not just at x is equal to 1, but at x is equal to some arbitrary value of x. So now the natural question of fractional calculus is, can I extend this value of n, which I've assumed to be a natural number, to the set of positive real numbers? So can we extend n to some alpha in the set of positive real numbers, and then what we would have instead of an iterative integral would be a fractional integral, right? So if we sort of approach it in the same exact way as before, in particular we're going to extend factorials via the gamma function and leave sort of everything else fixed as our analytic continuation, that means I of 0 to 1 of alpha of Tm is just going to be equal to gamma of m plus 1 divided by gamma of m plus 1, because we've already proved that, but now it's going to be defined, I guess you could say, for any positive real number alpha. right? So what we're going to do is we're going to extend this operator that we've defined to the set of real numbers. So let's first off recall that iterative formula. So before, we've already shown that the integral from a to x of f of t is going to be equal to 1 divided by m minus 1 factorial, integral from a to x of x minus t, m minus 1 f of t dt. And what we're going to do is we're going to take n, which at least for right now is going to be in the set of natural numbers, and we're going to extend this to an alpha in the set r, which is greater than or equal to 0. Technically, we're going to assume that alpha is greater than 0 because the zeroth integral or the zeroth derivative of a function should be the identity operator, so it shouldn't be doing anything to that. So we're going to extend that via this approach, and we're going to be extending the factorials via the gamma function because we have that present in this particular expression. So when we perform these extensions, we get what is referred to as the Riemann-Liouville fractional integral. So the Riemann-Liouville fractional integral via these approaches is going to be equal to IAX, and we're going to abbreviate that by RL in the top left-hand side, of alpha of f of t, and that's going to be equal to 1 divided by gamma of alpha. So you sort of see why we would like alpha to be greater than 0, not greater than or equal to 0. And that's just going to be equal to the integral from a to x of x minus t, alpha minus 1, f of t dt. So that is our first star. Now some people will allow alpha to be a negative integer per se, or even a negative number, but of course you have some interesting analytical properties to consider there, and maybe you have to investigate, well, what type of function f has to satisfy in order for us to define it for all real numbers alpha. But we'll consider that more advanced topic a little bit later, but for now we're just going to assume that alpha is just going to be a positive real number. Now let's look at a couple important examples of the Riemann-Liouville fractional integral. So for the first special function, I guess you could say, that we're going to consider the Riemann-Liouville fractional integral of would be a constant, but not just any constant, but the little constant 1, because we can just multiply 1 by any arbitrary constant c and get the Riemann-Liouville fractional integral of c, because AXRL is just a linear operator, so we could easily extend that if we wanted to. So let us assume we want to find the Riemann-Liouville fractional integral with an arbitrary base point a and terminal point x of alpha of 1. So if we just apply the definition of the Riemann-Liouville operator, that's just going to be 1 divided by gamma of alpha times the integral from 0 to a to x of x minus t to the alpha minus 1 times 1 dt. So what we're going to do here, so this is a nice little u substitution problem, so what we can do is we can just let u be equal to x minus t, so du is just going to be equal to minus 1 times dt, forcing the dt to be equal to minus du. So that's the first substitution that we need. So originally we have the variables t, which is equal to the interval a to x, so when we shift this to u, so when t is equal to a, then u is going to be equal to x minus a, and that's going to go to x minus x for the upper bound, which is just going to be equal to the interval x minus a to 0. So once we perform that transformation, then we have that the Riemann-Liouville from a to x of order alpha of the constant 1 is just going to be equal to 1 divided by gamma of alpha times the integral from x minus a to 0 of u to the alpha minus 1 times minus 1 du. This minus 1 can reverse those limits for that integral to make that a little bit more nicer, and that's just going to give us 1 divided by gamma of alpha times the integral from 0 to x minus a of u to the alpha minus 1 du. Keep in mind this alpha minus 1 is just a constant, and this is just a power rule for integrals. So that 1 over gamma of alpha isn't going to change, so 1 over gamma of alpha times, and then we're going to have u to the alpha minus 1 plus 1, which is just going to be equal to alpha, and alpha is the new power for that, and then we're going to replace u as going to x minus a, and then u is going to go to 0, which is going to eliminate 2, 0, once we subtract that. So once we have that, then we have the nice little rule that the Riemann-Liouville fractional integral from a to x of the constant 1 is just going to be equal to x minus a to the power of alpha over gamma of alpha plus 1. And you might be like, well, where'd that gamma of alpha plus 1 come from? Notice that we have alpha times gamma of alpha, which we know to be equal to gamma of alpha plus 1, which is one of the functional relationships for the gamma function that you definitely should be familiar with. So we can apply this to technically any function, but what I want to do now is introduce a new operator, which is called the Riemann-Liouville fractional derivative. So the Riemann-Liouville fractional derivative. So what we're going to do is we're going to take the Riemann-Liouville fractional integral and mirror it. So what we're going to do is we're going to send alpha to minus alpha, and we're going to denote I minus alpha to be equal to d alpha. So once we do this, then we can get a nice little property from the fractional derivative of 1. So we have that the Riemann-Liouville fractional derivative of ax of order alpha of the constant 1 is just going to be equal to x minus a to the minus alpha all over gamma of 1 minus alpha. Right? So clearly we see that we have some restrictions. In particular, alpha must belong to the interval 0 to 1. In particular, what we can do is we can let a be equal to 0 to get a particular family, and then you should be able to prove the following theorem, in particular the Riemann-Liouville fractional derivative with base point 0 and terminal point x of a arbitrary constant c, where c is any real number, is going to be equal to c divided by gamma of 1 minus alpha times 1 over x to the alpha. Again, alpha belongs to 0 to 1. Now this relationship should look extremely familiar. This is the same exact result we got from simply extending the factorial via the gamma function in the power rule for monomial functions. It is the same exact thing. So I didn't really give it a name at that point. We're just like, oh, we're just extending the factorial via the gamma function and creating sort of an operator with that. But we see that that extension, at least in that case, is precisely the Riemann-Liouville fractional derivative of that monomial function, which is actually pretty interesting. So let's see if we can actually formally prove that result with the definition of the Riemann-Liouville function, just to make sure that that actually is the case and the constant function just doesn't happen to overlap with that result for the constant case function example. So Theorem 2. Let's prove that the base point 0 Riemann-Liouville fractional integral of t to the power of n is actually equal to gamma of m plus 1 over gamma of m minus alpha plus 1 times x to the m minus alpha, where alpha is restricted to the interval 0 to m plus 1. Right? So let's do a nice little proof of this result, because I think this is actually it sort of starts to bring things together, and because this is the first real operator of fractional calculus that you definitely should be familiar with. So d0x Riemann-Liouville alpha of Tn, at least from the definition, is going to be equal to what? So alpha is going to be arbitrary, n is going to be fixed, and then we're going to have that this is going to be equal to what? So once we look at the definition, that's just going to be equal to 1 over gamma of minus alpha times the integral from 0 to x of x minus t to the minus alpha minus 1 times t to the n dt. So what we want is we want this integral to sort of be represented as a beta function. So we somehow need to make that x turn into a 1, right? So we want to send the interval 0 to x, and we want to map it to the interval 0 to 1. So the easiest way to do that is if we have the transformation u is equal to t divided by x, right? So this is the t interval and this is the u interval, right? Because when t is equal to 0, u is equal to 0, and when t is equal to x, x divided by x is equal to 1, provided that x is not equal to 0, which we're assuming not true, right? So once we perform this transformation, u is equal to t over x, that means t is going to be equal to ux, and dt is going to be equal to, keep in mind x is a constant, so that's just going to be x times du. So when t belongs to the interval 0 to x, u is going to belong to the interval 0 to x divided by x, which is the interval 0 to 1, provided that x is going to be greater than 0. Also, let's write this in a slightly different way because we need to transform all of the pieces of our interval. X minus t is going to be the same as what? So t is replaced with ux, so we're going to have x minus ux, and we can factor that to be represented as x minus 1 minus x times 1 minus u. So once we perform those transformations, what will we get? So we have the Riemann-Liouville fractional integral of order alpha with base point 0 of x of the polynomial function t to the m is going to be equal to 1 divided by gamma of minus alpha, new bounds of 0 to 1, and then we're going to have our x 1 minus u to the power of minus alpha plus 1. It used to be minus alpha minus 1, but I'm actually going to shift it into this form. And then t was equal to ux, so we're going to have ux to the power of n, and then we're going to have x du as our differential once we differentiated it. So what do we have here? So everything that doesn't have u in it is technically a constant. So what do we have here? So we have an x to the power of n located there, and we have an x to the power of minus alpha plus 1, so we can factor those things out. Right? Oh, and we also have that lonely little x there at the very end. So once we pull all of that out, what will we get? So we're going to have 1 over gamma of minus alpha, x to the minus alpha minus 1 times x to the power of n times the integral from 0 to 1 with everything that has u in it. So that's going to be equal to 1 minus u and then minus alpha minus 1 and then u to the m plus 1 minus 1 du. So notice that this is in beta form because we have something minus 1 and something minus 1. So this is precisely equal to a beta function evaluated at minus alpha and n plus 1. Let's also keep note of a nice little transformation of what we're doing here. In particular, minus alpha minus 1 plus n is just going to be equal to n minus alpha. Right? And you should know where this is sort of going to come from, right? So let's take a moment and think about that. So you should be able to see here what I'm doing. I'm actually just combining the minus alpha minus 1, the 1, and the n exponents because we're multiplying those together, and we sort of need to know what that is going to result into. So once we have that, that's going to give us 1 divided by gamma of minus alpha times x to the n minus alpha, so that's a good sign because we know that that's supposed to be there. And then times the beta function evaluated in terms of gammas, we're going to have gamma minus alpha, gamma of m plus 1, all over gamma of the sum of those things, which is going to be n minus alpha plus 1. So what do we have here? So notice we have a gamma minus alpha there, a gamma minus alpha there, so they're going to eliminate, which is a very good sign. And then we're just going to be left with the constant of gamma of n plus 1 over gamma n minus alpha plus 1 with a polynomial with difference exponent n minus alpha, which is what we desire to prove. So let's just formally state that again. So the Riemann-Liouville fractional integral with base point 0 of x of t to the power of m is equal to gamma n plus 1, gamma n minus alpha plus 1 times x to the n minus alpha. And of course you should be able to show that alpha must be restricted to the interval 0 to n plus 1 for all these integrals to converge appropriately. Right? So that's a very, very good result. Now there's one other thing we haven't proven, because notice that we were able to prove a very special relationship for the derivative of an exponential function, right? So let's just formally state that. So is the Riemann-Liouville fractional integral of alpha of 0 to x of e to the lambda x, is this equal to lambda to the power of n, x to the m minus alpha, times the Mittag-Leffler function with parameters 1, n minus alpha plus 1, of evaluated at lambda x for some given alpha. Because these other two properties that we sort of proven here for the Riemann-Liouville fractional derivative and integrals were just simply proven via extending factorials to gamma functions and sort of leaving everything else fixed. And using that same exact extension, we were able to prove that this is actually also true if we extend factorials to gamma functions. So if that is the case, since the other two properties satisfy for Riemann-Liouville, does this property also satisfy for the Riemann-Liouville? We'll get to that in the next video, but until then, I hope you take care. Thank you.